So I wrote our little discovery here. What this equation says is that the sum of all of the coin scores equals the number of pairs that show up here, which equals all of the possible head-tail pairs when you map every single head in the sequence with every single tail in the sequence. And I'm going to do a small proof and prove to you that it is indeed true that if you take an arbitrary head-tail pair here, it's going to show up once and only once in this set of pairs. And if I prove that to you, then this equation is indeed true, and we will have our answer. We will have 95% of our answer. The 5% left would be just doing the computations. So I'm going to write down what I want to prove. Let's see. I'm going to erase this part now. So in order to prove that all of these head-tail pairs show up here, the first thing I'm going to prove is that for an arbitrary head-tail pair, so I'm going to denote that with H subscript X, T subscript Y, where X and Y can be have to be greater than or equal to 1 and less than or equal to the number of heads and tails in the sequence respectively. So for any arbitrary HXTY, HXTY must show up either under HX or under TY when I'm calculating the scores. Now if I prove this, this will not be enough, because if I prove it, what I'm saying is that every pair here has to show up here, but there's no guarantee that it only shows up once. What if it shows up twice? So that's the second thing I'll have to prove for my proof to be complete, is that HXTY, or actually I can rather just add it to the first statement. So for any arbitrary HXTY, HXTY must show up under HX or TY when calculating scores. It cannot show up under both. I'm not going to be doing a rigorous proof, so I'm just going to talk through it. It should be very intuitive, actually. So if I choose any HXTY, how do I know that it must be under HX or TY? Well, for any head-tail pair, let's just choose H3, T1 for instance. It's either going to be under H3 if T1 is to the left of H3, or it's going to be under T1 here if H3 is to the left of T1. And given a sequence of coins, one of these cases has to happen. Like if you're given a sequence of random heads and tails, and you have one head and one tail, one of them must show up to the left of the other. So going back here, I have H3 here and T1 here, it must show under one of these, and in this case, since T1 is to the left of H3, it shows up under here. So that proves the first part, that it has to appear here. And the proof that it cannot show up under both is very obvious, because if T1 is to the left of H3, then obviously H3 cannot be to the left of T1. That's why every single pair here shows up once and only once here. Now that we're done with the proof, we can actually go back to getting our numerical answer. question says, adding up all these numbers, you get 136. This 136 is the H-score. So what we're given in the problem is the H-score equals 136, and we're given that the T-score equals 153. Now we have this key piece of information at the bottom. How do we apply it to what we're given? Well, the sum of all of the coins' scores equals the H-score plus the T-score. So H-score plus T-score equals, now if I add these two up, I get 289. So we know that the number of heads times the number of tails should also equal 281. Now the number of heads and the number of tails must be positive integers. What are all of the possible factors of 289? I'm going to list them. So 289, if it's not obvious, it is 17 squared. So it's 17 times 17. However, we cannot forget about two other important pairs. 289 is also 289 times 1, as well as 1 times 289. Now, this is different from this because the left side, the number on the left side represents the number of the heads, and the number on the right side represents the number of the tails. So when I reach the conclusion that the number of heads times the number of tails equals 289, that also helps me reach this conclusion that my sequence can consist of one of these possibilities. So it can either have 17 heads, 17 tails, or 289 heads, 1 tail, or 1 head and 289 tails. All of these possibilities satisfy this condition right over here, that the H-score is 136 and that the T-score is 153. So how do we know which one is right? Well, if you go back to the question here, the question gives us another key piece of information. Another piece of advice for generally solving any Mathly type problem is that use every single given information you have, because they're not just giving it to you for fun. There's a reason why they're giving it to you. And if you have an approach in mind that doesn't require every single piece of detail the problem gives to you, 99% of the time you have the wrong approach. So think again. Now it says that the first two coins are heads, tails. So I'm going to write that down. What I have to do here is either prove that one of the cases works or prove that two of them don't work. It's always going to be easier to disprove than prove. So I'm going to disprove two of them. Going on the second case, if I have one tail and I know my sequence starts with head, tails, that means the rest of the sequence has to consist of only heads. So it's going to be head, tail, and then 288 heads that follow. In this case, my T-score would be just the number of heads to the left of this single T. So that's just 1. But the question said that the T-score has to be 153. So that automatically rules out this possibility. Similarly, if my sequence starts with head, tails, and have 1 head, that means this 1 head should be followed by 289 tails. And in this case, my H-score would be the number of tails to the left of this H, which is 0. But my H-score should be 136, not 0. So this is ruled out. And that automatically leaves one possibility. The possibility is that I have 17 heads and 17 tails. We're almost done. The question says find n, and n represents the total number of coins in your sequence, so I just add this up, and I get that n equals 34. There. Thank you so much for watching, and I Hope you found this question to be interesting. If you did, don't forget to subscribe. Thank you so much. Bye!